Welcome guys to this video about the derived function. Now you might recall from the work that we did in class today that we were having a look at the idea of limits, and this work on the derived function basically uses the idea of limits to come up with a definition of what this is about. Now essentially what we're after is if we have some sort of graph that's curved. Let's say I was interested in the slope at that point, and let's label it A. Now we can see that the slope is changing. Now slope, you might recall from previous years' work, is an indication of how steep the graph is. And we have zero slope, we have pretty low slope, and as it gets more steep, okay, the value is getting higher and higher and higher. The value, yes, because the gradient or slope, you might recall, another word for this is gradient, is measured with a number. Okay, and as we get more and more steep, the value of the gradient is getting larger and larger until you get a vertical line, and it's meant to be vertical, where it's so steep that it's undefined, or you could say infinitely steep. And we also have slopes which go downwards, and these are negative slopes. Okay, so if I was interested in the gradient at that point, well, how do we measure gradient again? Well, if you recall from previous year's work, if I have a line, and if it's a straight line, then I can measure the gradient in this way. Okay, let's take a practical example here. Let's say this is the point 2, 4, and this happened to be the point here, let's say 5, 7. Then a measure of the slope was defined to be this vertical distance, which is sometimes called the rise, or the change in the y direction, and this horizontal distance between the points, sometimes known as the run, or more accurately really, the change in the x direction, or the slope, was defined to be the rise over the run, or the change in y over the change in x. So for example, the slope here would be 7 minus 4, that 7 value here, minus that value there, giving us the rise, and the run would be 5 minus 2, which happens in this case to equal 3 over 3, or 1. Excuse me, got a bit of a cold. Okay, so yeah, that was the basic idea of how we calculated the slope. And if we did this in a more sort of general sort of way, let's put our missing line back in there a bit. Okay, and if we called this point here x0, y0, and this point here x1, y1, then the slope, which commonly has the symbol m, you might recall, was change in y over change in x, or y1 minus y0 over x1 minus x0. And then this led on to other sorts of coordinate geometry work which you might have done in year 12. Okay, so yeah, that's just a quick review of how to calculate the slope. So what has that got to do with the derived function? Well, the derived function is a function which is going to allow us to get the slope at any point on our original curve here. So how would we do that? How would I find the slope at this point because it's not a straight line, so the slope's changing all the time along here. So how do I get an idea of the slope at this point? Well, let's swap over to a different program which is going to allow us to explore this a bit more. Okay, and the program I'm using, I've just got the website for it open here, is called GeoGebra, and it's a free download available for all these different platforms here. And let me just fire this up. Okay, and we're going to use this to explore, trying to get the slope at a point. Okay, so here's our basic interface, and down here is where we can graph things. Unlike Graphmatica, this particular program allows us to do a lot more geometry work than what that one would allow us to do. Alright, so I'm going to move this a little bit more centered, and what I'm going to do is I'm going to put a point on this parabola here, the basic parabola y equals x squared. Now let me just zoom up on this a little bit. Oops, I don't want another point. Let me delete that. Okay, and let me just try and change the scale a little bit. Okay, so just recentered things a little bit more. Okay, and so here's our point A. Now I'm interested in the slope at that point A. Now one way we could explore this is, let's put another point somewhere here. And what I'd like to do now is to draw a line between those 2 points. Now, unfortunately, we're going to lose our axis at some stage here, although it's still here, but I need to focus on this region here. Now here's the equation of the line joining the 2 points here, and I'm going to put that in a form which we're more used to from, say, our year 11 sort of geometry work or straight line work. Okay, so here it is, y equals 3.87x minus 3.68. You might recall from previous year's work that that value in front of x there tells us the slope of this line here, 3.87. Now, what I'd like to do is, you might notice that that line sort of hugs that curve pretty nicely, and that line is not a bad idea of what the slope would be at point A. Now, I think we could get a better idea of what the slope at point A is, maybe if I could move point B a bit closer to A. Okay, and so notice the slope here is changing as I move B closer to A. And one other thing I'd like you to focus on is, remember that definition of the slope, the change in y over the change in x here. And as I move B closer to A, one of the things which is changing is this horizontal distance is getting less. Yeah, sure, the vertical distances as well, no doubt about that, but do appreciate that the horizontal distance is also getting smaller and smaller. So if I zoom up a bit more, notice that that line joining A and B very much now, hugging that curve because we're zoomed in so much here. And if I move B closer and closer, okay, so once again we're getting this horizontal distance getting tiny here. Let me zoom up a bit more. So making B closer and closer to A. Notice that this slope now 3.38. Let's Let's move this closer in again. Okay, it's changed to 3.34. Let's zoom in up even further. Horizontal distance getting tiny. Remember, I'm zooming up so that distances are actually smaller than what they appear here because of the zooming in factor. Okay, notice that there that slope's not changing very much anymore. 3.33. Okay, let's zoom up even further and let's move point B. Okay, notice how that slope's basically staying at 3.33. Okay, so move it closer. Is it going to change? No, let's put it right on top there. Okay, so it looks like the slope at point A is 3.33. Okay, so what was going on here? Well, let's just swap back to this view here and have a bit of a talk about this. Just grab some other bits of hardware. Okay, so let's go to another page here. Alright, so what we had was we had this, oops, that was meant to be a vertical line, pretty horrible one, wasn't it? Okay, so we had this situation like, not like that, that's hopeless. Let me try and do that again. Apologies about the delay here. Okay, that'll have to do. And we had this curve like this. Alright, so I was interested in the slope at point A. Now what we did was we took a point B and let's imagine that line joining A and B, going through there. Okay, so the slope of the line AB, and I'll call it M for slope. Okay, so that is going to equal, let's call this point y1, and that's y0, and let's drop this straight down here. That's x0, and that is x1. Okay, so the slope y1 minus y0 over x1 minus x0. So what we were doing was we were basically reducing this horizontal distance here. Okay, so let me just label things in a slightly different way so things match up more with what's in your book. Okay. Still the same idea though. Okay, so let's call this point X, and this one will say that this is y equals some function of x, not just the good or quadratic, but just a function of x. And so this point here would be whatever the y value is when I put x into the function. So this is the f of x value. And let's call this x plus h, okay, where h is that distance between here and there. And so this point here would have a y value of fx plus h. So put x plus h into the function, calculate the y value, so that's what that is. So this slope, another way of representing it then would be, well, y1 is this fx plus h, and y0 is this fx over x1 is x plus h, and x0 was x, so take away that, and of course that simplifies a little bit. Changed my notation, haven't I? And that was actually the correct one down the bottom there. The slope of the line AB, written like that. Okay, so this simplifies too. Now what we did, if you can remember back to that GeoGebra video, was we made B come closer and closer and closer to A, and we zoomed in and in and in and in until basically we were so far zoomed in we saw that this line and this sloped curve essentially had the same slope at point A, but only when we had zoomed in considerably. And when we zoom in considerably, this distance h is becoming smaller and smaller and smaller. And what do we call that idea of we're zooming in and we're having a look at around a point? Well, what we're doing is we're taking the idea of the limit. What is happening to this as we make h approach 0? And well, we can see from that video, we know what happens. We know that this straight line and this curve end up having the same slope as long as h is tiny, close enough to 0 in fact. So this is what the definition of a gradient is then. So the gradient at point x is the limit then, remember that notation, as h approaches 0 for this function. Okay, and that's what the definition of a gradient is, or the derived function. So this here is known as the derived function equation. Okay, so we'll explore this more with some examples tomorrow. Would be perhaps worthwhile having another look at this, especially the idea of, you know, how we get the slope of this straight line joining A and B equal to the slope of the curve at point A, which is that tangent line. Okay, as we bring B closer and closer to A, and this horizontal distance becomes infinitesimally small. Okay, so it's basically approaching 0. That's when those two would have the same slope. Okay, and so this is where this definition then of the derived function comes from. Alright, so that's it folks. We'll catch you tomorrow where we can discuss this in a bit more detail.